Okay, so our project was on loan default prediction by Ryan, Vadeep, and myself, Aryan. We're going to start off with background, we'll move on to dataset, EDA, preprocessing, modeling. Starting off with the background, the data of financial information used to predict whether a borrower will default on their loan. Basic information. The dataset contains records of property loans, homes, commercial, etc., into account various factors such as borrower, demographics, information about the loan. Moving on for the data set, there were 33 attributes that can be grouped into three main categories: borrower information, loan information, and property information, each having about borrower having age, gender, income, loan information having amount, type, purpose, interest, and more. And then finally, the property information having property value, type, units, and more. In about total, we had 148,670 records. Now, reducing the data sets, the steps taken was that it was reduced to 20,000 records for computational efficiency. We undersampled the data set using target variable. The impact of this was that there was enhanced model performance while reducing computational overhead. Moving on to the EDA, as you see, we have a couple of images here. There's a presence of the integer and float and object data types, which shows both numerical and categorical data. We also have, as you can see, the varying non-null counts that shows the presence of missing values there. And then both of these issues will obviously be addressed later on. But first, let's examine our categorical data first. This is our categorical data, which has a presence of highly imbalanced features. The next step would be after this to employ encoding techniques and consider balancing strategies for our data. Now over here we have binary, nominal, and ordinal. Binary being that has two unique values, for example, yes or no. Nominal being multiple unique values without any particular order, which would mean, for example, loan purpose. And ordinal data, which shows a very meaningful order, such as age groups. Now, as we look into our numeric data, there's many skewed and non-normal distribution graphs over here. Moving on, we have long tails. The long tails suggest significant variation requiring scaling or transformation. There's also outliers detected and that were present, which means it's present in 9 out of 10. We found out it was present in 9 out of 10 numerical attributes that contain the outliers. And then the major presence of missing values for some attributes, you can see as we have a graph over here, which the observation was that several attributes exhibit significant missing data. The impact of that was that the missing data can compromise model accuracy if it's not addressed properly. An example of a solution that we can provide is that strategies like imputation or advanced methods, for example, k-means imputation, could be explored possibly for preprocessing.
So now we move on to pre-processing our data. Let's again start on the categorical side. And the first thing we need to do is handle the missing values. So we observe the distribution of the missing values. And we notice that the data is either highly imbalanced, such as the loan limit, or has an insignificant amount of null values, such as negative amortization. Therefore, we feel comfortable replacing the null values with the most frequent occurrence or the mode. And that's our code. Now we move on to encoding our categorical attributes. Recall that we have three types of categorical data, which are binary, such as security type, nominal, such as loan purpose, and ordinal, such as age. So we will encode these in different ways. For binary, we use one-hot encoding, which maps indirect to 0 and direct to 1. Nominal, we use dummy encoding, which makes a binary for each purpose. And ordinal, we use ordinal encoding, which maps the values to a range of integers. That's our code. Now onto our numeric data. We first need to again handle the missing values. So recall the scope of our missing data. Large quantities of missing values per attribute and attributes with missing values makes dropping either records or attributes unwise. Additionally, irregular distributions make simple imputation via mean-median mode either infeasible or inaccurate. So our solution is to use k-means imputation, which means using a k-means algorithm to fill in the missing values. And we can see the results here where we compare the original distribution, filling the missing with the median and filling the missing with k-means. We can see that if you try to fill in the missing with the median, the data loses its original shape as all the values just go to the second bar there. But when you fill with k-means, what it does is it tries to predict the value of the missing variable by looking at other variables, which lets it get a more accurate imputation and more closely preserves the shape of the original data. So now we have to scale our data. Recall that many of our attributes have a large presence of outliers. We want to keep these outliers because they're valuable indicators, but we still need to scale the data to balance out our features. So our solution is to use robust scaler, which scales by using the interquartile range. And we can see the results here where all the features are scaled to a median at 0. Now moving on to dimensionality reduction, reducing attributes. We can instantly remove 3 attributes, which are ID, year, and secured by, because it's equivalent to another variable. And so we will now look at a correlation heat map between attributes. We observe that the data is mostly uncorrelated here. There's a lot of grays, which makes principal component analysis unadvisable. However, we observe 2 instances of strong correlation that we can drop attributes for. So we drop 1 attribute for each, which ends up being construction type and loan type 2. So now we summarize our results looking at the beginning data versus the final data. We can see in the beginning there was a lot of object types which show categorical text data. The final data, none of that's there. Everything is float 64 numeric. In the beginning, we also see that there was a lot of missing values which are not present in the final. Everything is at 20,000. And also in the final, there happens to be a bit more attributes. There's 42 just because of the way we encoded our categorical. So now we move on to modeling.
Hello guys, my name is Wadi and I will be presenting the modeling part of our presentation. First of all, we will look at the logistic regression model, which has a accuracy rate of 0.78, as well as the ROC curve graph, which has the positive rate to the false positive rate, including the precision, recall, F1 score, and support numbers. Here, this is the graph of the logistic regression, and it has the upfront charges to the rate of interest. Here we have the KNN model, which has an accuracy rate of 0.79, which is higher than the logistic regression model that we previously just shown, and the ROC curve, which has a visual difference. Here we have the SVM model, which has a lower accuracy rate than both the logistic and the KNN, coming at a 0.71 accuracy rate, and the ROC curve as well. The previous models unfortunately had low accuracy due to not being able to handle mixed data well. However, now we will look at decision trees, which should perform better. So this is the decision tree classifier, which has an accuracy rate of 0.89. You can see visually from the ROC curve here the difference, as well as the precision, recall, F1 score, and support numbers. So this is the smaller decision tree to visualize data, and it has a 75% accuracy. This is the model. And we notice that credit type equity is equal to 1, which strongly suggests that defaulting on a loan. Here we have the random forest model, which comes in at an accuracy rate of 0.89. The support numbers as well, and the ROC curve. Here we have the random forest top 10 most important features. The credit type equity coming in at number 1, rate of interest coming in at number 2, then upfront charges, LTV, interest rate spread, and so on. The credit type equity coming in at 0.175 feature importance score. Then we have the bootstrap aggregator model, which comes in at a 0.94 accuracy rate, as well as the ROC curve, which has a visual difference. Here is the bootstrap model, most important features. Again, we have credit type equity at number 1, rate of interest at number 2, upfront charges at number 3, and so on. Credit type equity coming in at over 0.2 on the feature importance score. Here we have the gradient boosting model, which comes in at a 0.959 accuracy rate, as well as the ROC curve again. And for the gradient boosting model, most important features, we have credit type equity again at number 1, then neg amortization, lump sum payment, rate of interest, and so on. And credit type equity comes in at 0.6 on the feature importance score. Then we have the cat boost model, which has the highest accuracy rate at a 0.969%. Then we have the ROC curve visually here, coming in at a right angle almost, and the supporting numbers with it. And for the cat boost, most important features, we have rate of interest coming in at number 1, which is different from the others because credit type equity here is at number 2. Then upfront charges, interest rate spread, LTV, and so on. So as we said, the most important feature is interest rate for the cat boost model, which is different from the previous models because credit type equity was practically at number 1 for all the other ones. And this is the visual graph for the cat boost model, the upfront charges to the rate of interest. And this is the visual difference of the cat boost versus the regression model that we did in the beginning. And in conclusion, credit type equity and rate of interest appear to be the most important predictors of defaulting. Cat boost is the most accurate model, however, bootstrapping may generalize better to unseen data due to having high importance for more variables and having a less extreme prediction distribution. Thank you guys.